So it's my great pleasure this morning to introduce our speaker, Thomas Venner. Tom received his PhD in 1993 at the University of Augsburg in Germany. He did postdocs in Augsburg and at Georgia Tech, at Georgia Institute of Technology. After that, he joined the Applied Mathematics Department at the University of Maryland in Baltimore County in 1998. Since 2002, he's been at George Mason University, and Tom's research focuses on dynamics of partial differential equation, random and stochastic dynamical systems, as well as computational topology and its applications, and of course, computer-assisted proof in nonlinear analysis. So Tom, thanks for speaking today, and the floor is yours.
All right, thanks. Well, thanks, Jay, for the invitation. And also thanks, Jean-Philippe and Jan Bouwe and Jay, of course, for organizing this session or this online seminar. I've definitely been enjoying the talks. Couldn't really attend that much this semester because of teaching, but I've definitely been enjoying it so far. We'll see what happens today. So I'll be talking about computer-assisted proofs in the Ohta-Kawasaki model. This is something that there have already been a number of talks in the seminar over the last 1.5 years. And I'm not going to assume that anybody in the audience has seen those talks, so I will definitely give the provided background. Just at the outset right away, this is joint work with Ian Johnson. He was a former undergraduate student of ours. Jean-Philippe was part of some of the work, and Evelyn Sander, my colleague here at George Mason. All right, so let's get started. So I'll be talking about microphase separation in Diblock copolymers, in particular about bifurcation diagrams and doing computer-assisted proofs in the context of for these bifurcation diagrams. But I do want to give a little bit of a background of where these models are coming from. Diblock copolymers, they're soft materials that are really characterized by very interesting pattern formation phenomena. This is due to the fact that these materials are made out of large macromolecules. They're basically two chains. There's two different monomers, types A and B, let's just call them. And those chains, you can see them here. They're shown in blue and in red on in this picture. They're basically
you don't see the picture.
Oh, you can't see the mouse?
No, and also I think you're not full screen, so I'm not sure if
I'm full screen actually, at least here.
We still see the title slide actually.
And we see the the bookmark in the top.
Oh yeah. Let me quickly get out of here again. Try it again.
Yeah, now we see the.
And full screen again. Do you see it now full screen?
We don't see it full screen.
No, nothing happened for us.
That is very bizarre. But you do see it sort of on the normal.
Yeah, now we see at least the other slide. Yeah.
Maybe I should just leave it that way. I have no idea why it doesn't work full screen. I've had some issues with Adobe Acrobat recently, but is this good enough?
Yeah.
Yes, we can see. Yeah.
Okay, perfect. All right. So, and now you see my mouse also?
Yes.
Perfect. Good.
That's right. Yeah.
All right. So the microphase separation is driven basically by chemical incompatibilities that we have between these two different monomer blocks. And the way this actually works is the following. Let's assume for now that you would have these two monomer blocks separately in the copolymer melt. If they were not covalently bonded, then basically they would separate because of thermodynamic forces. They would basically separate like oil and vinegar and salad dressing. But since they are covalently linked together, basically that is a counterforce that sort of avoids that global separation. And this leads to interesting patterns. You can use theories from physics like self-consistent mean field theory to actually predict what kinds of equilibrium structures you would see. This will depend on this parameter Fa, which is the degree of polymerization. So basically, it's the length of polymer A divided to the whole length of those polymer chains. And depending on what that fraction is between 0 and 100%, you basically see different kinds, or would expect different kinds of global minimizers for the phase separation. So you see spherical global minimizers, cylindrical structures, then there's these very interesting gyroid, double gyroid structures. Then sort of at close to the 50-50 split, you will see lamella, and then basically the thing turns again in the other direction, and you see these other global states. Now these are all global energy minimizers that are predicted by self-consistent mean field theory. What's really interesting about the equation, that's really what I'm going to be focusing on much today, is that the equation itself has multiple stable states. There's metastability to a very, very high degree. And one of the things that we're interested in and that we've been trying to study over the last few years now is trying to understand where do you actually end up if you just look at the dynamics of this equation. Are you really going to get to global minimizers? Or are you maybe trapped already ahead of time in some local minimizers? And so this is what I'm roughly going to be talking about today. So this is a brief outline. I'll spend a little bit more time talking about the Diblock copolymer model, what it is. I'll provide some numerical evidence of long-term dynamics and what it has to do with the attractor structure. We'll talk a little bit about equilibrium structure of the model. And then basically for the next three parts, I'm going to be talking a little bit about the framework that we're using for the computer-assisted proof setting. Basic goal is we'd like to validate these bifurcation diagrams that I'll be showing you. We sort of have a very specific point of view that we're using to do these validations based on a constructive version of the implicit function theorem. So I'll go through this fairly quickly. I know some of you people have seen this already. And then the sort of second half of the talk will be roughly about validation of bifurcation points. In particular, one of the things that we'll be seeing is that we'd like to be able to trace out curves of bifurcation points, especially of pitchfork bifurcation points. I'll talk a little bit about results that we've had together with Jean-Philippe on saddle node and Z2 symmetry breaking bifurcation points. And then at the very end, last third of the talk maybe, is going to be talking about bifurcation points that we couldn't address in the paper with Jean-Philippe. It was not standard Z2 bifurcation, and we've been thinking about this for a while now, and I think we finally know how to do it. And as usual, it was much easier than one thought it would be, but we think it's some interesting results. All right, so let me get started. The Diblock copolymer model is a fourth order PDE. It's a fourth order PDE for an order parameter U. And what you should think of as U is really just the difference in concentrations of these two monomers. So if U is equal to +1, that corresponds to monomer A being prevalent at that point in time and space. And U equals -1, that means, or close to -1 means that we have monomer B. It's a fourth order PDE. We study this equation with homogeneous Neumann boundary conditions. Those are the boundary conditions that were originally proposed for the equation. What you also notice here, this equation looks very similar to another famous equation called the Cahn-Hilliard equation. This is sort of the first part here. Epsilon is a small parameter that models interaction length. And what's really distinguishing the Ohta-Kawasaki model from Cahn-Hilliard is that there's this negative linear term that's coming in. Sigma, this parameter, models the polymer length scale. And also back here, the parameter mu, that gives us the total conserved mass in the equation. Omega is just a bounded domain. We're going to be studying it for this talk, mostly on a one-dimensional domain. And then the nonlinearity, I wrote down f of u as u minus u cubed. That's the standard nonlinearity, but pretty much everything that I'm going to be saying today also works if we have any odd nonlinearity that looks qualitatively the same as u minus u cubed. So this is not specific about that nonlinearity. Now this equation has been studied quite a bit. Some properties that I just quickly want to run down. Obviously, if I take u of tx identically to mu, that is an equilibrium solution. That turns out to be unstable if f prime of mu is positive and epsilon is sufficiently small. And basically what we're interested in is exactly that phase separation phenomenon. If you start close to this unstable state, that's what would happen if you're at a high temperature polymer melt. Once you lower the temperature, the dynamics is starting, and the question is where do you end up in terms of the long-term regime. The equation conserves mass. It has an energy functional associated with it. So this is the standard van der Waals free energy functional that you have in the beginning. And it's basically amended by this sort of non-local term with this inverse Laplacian root. And that really is responsible for these macrostructure pattern formation effects that we can see. And this capital F of u, that's just the negative antiderivative of the nonlinearity. So that's just a double well potential. Interesting for us is going to be the equilibrium structure, in particular the structure of minimizers, local and global minimizers of this equation. And for the remainder of this talk, I'm really going to be considering only the one-dimensional domain case. There are results in higher dimensions. Even some of the things that I'll be talking about today also work in higher dimensions with little change, and certainly the estimates we've set up to work also in higher dimensions. I definitely want to point out work by Jan Bowie, J.F. Williams, and others, where they have wonderful papers from the last few years where they really talk about 2- and 3-dimensional structures and associated bifurcation diagrams. So there is work done in higher dimensions, but we're going to have a very, very specific focus here today. So the starting point for all this, also for my interest, was this paper by Nishura and Onishi in 1999. They've proved that if you consider a 1-dimensional domain for the Diblock copolymer model and fix the polymer length scale sigma, in the limit, as epsilon goes to 0, the number of local minimizers for that energy functional goes to infinity. So you basically have an energy that is extremely rough in the sense that there's all these little equilibrium solutions where you could get trapped in terms of the dynamics. There is a global minimizer. You can show generically that there's a unique global minimizer up to multiplication by -1. But the question is, when you look at the dynamics, are you going to get trapped before that? And a while back, Evelyn, Sandra, and I asked our undergraduate student, Ian Johnson, to try to do some numerical simulations to get an idea of what the long-term limit actually is going to be when you start simulations close at the homogeneous equilibrium. And what he noticed is that, so what's shown here in that diagram is as a function of the parameters sigma and lambda in the Diblock copolymer model, he basically took randomly chosen initial conditions close to the homogeneous state, followed them until they converged to an equilibrium, and just noted the periodicity. It turns out that all of these solutions converge to periodic limits, long-term limits. And what he noticed is that these very sharp delineating curves that basically where the periodicity switches from one wave number to the next. And the big question now is, what does that have to do with the actual equation? Can we somehow predict as to where these periodicity switches are happening? There was no obvious thing at the time to really understand where this might happen. Of course, one would think that it has to do with the bifurcation structure of the equation, and that's really what we're going to be spending pretty much all the time today in the talk talking about. In order to understand the dynamics, you have to look at the global attractor of the equation, and for that, of course, we need to find all its equilibrium solutions, and in particular their bifurcations. Equilibrium solutions satisfy this 4th-order elliptic stationary problem. We basically just said U of t equal to 0. We still have the homogeneous Neumann boundary conditions. We still have the mass constraint. In terms of bifurcation analysis, it's just easier to study a parameter that's large and goes to infinity than one that goes to 0. So instead of phrasing everything in terms of epsilon that was in the original equation, we're going to be dividing everything by epsilon squared and consider this new parameter lambda. So we're interested in what happens as lambda becomes large in terms of the bifurcation diagram. And that bifurcation diagram, of course, is related to the bifurcation diagram that you have for Cahn-Hilliard. I've already told you before that if for sigma equal to 0, this reduces to the standard Cahn-Hilliard equation. And for the standard Cahn-Hilliard equation, the bifurcation structure is known. Precisely, that has been proved rigorously. You have a trivial solution line, if we're in the case mass equal to 0, and you have at well-defined points that are exactly happening at k squared pi squared, for k an integer, positive integer, you get these bifurcating branches. These are always doubly covered branches. Color-coded here is the index of the solution, so we get stable solutions, index 1, index 2, 3, 4, and so on. And what you notice that when you're turning on sigma and make sigma positive, you suddenly get much more complicated bifurcation structure. There's an abundance of secondary bifurcation points. Obviously, that has to happen if we're going to be having unboundedly many local minimizers as lambda goes to infinity. The question is, how do we actually get from this Cahn-Hilliard model bifurcation diagram to the bifurcation diagram for the Diblock copolymer model? And let me show you a movie here. So what you're seeing in this movie is basically, as we're slowly increasing the sigma parameter from 0 to, I think, 10 in this movie, these bifurcation branches start to move. And in fact, what's happening is that the leftmost bifurcating branch basically moves through all the other branches, moves off to infinity. It actually disappears into infinity at a finite value of sigma. And as it's moving through, it basically is starting to pick off some of these secondary bifurcation points from one branch after another. And once you've basically sort of annihilated that first branch by making sigma sufficiently large, basically the picture repeats. You really get sort of a self-similar structure here where you're now looking at a bifurcation diagram that still looks very similar. I'm going to put it up here. But where after sigma larger than, I think it's pi squared in this particular case, the periodicity along each of those branches has changed. Now the first branch, you have 2 transition layers, then 3, 4, 5, and so on. Basically, this picture repeats. Now, why did I show you this example? Clearly, we do have multi-stability. That's, you can see here on the right in the image where I show the bifurcation diagram with respect to the energy on the vertical axis. And you clearly have multiple stable states. What is responsible for these sharp delineating curves when we're looking at the long-term limits of solutions starting at the homogeneous state? And it turns out that these secondary bifurcation points that sort of introduce these stable solutions, if you trace out these secondary bifurcation points in the lambda sigma parameter plane, they are exactly the ones, these delineating curves where the stability changes. So bifurcations that are actually happening far away from equilibrium, in some sense, are responsible for trapping a lot of these solutions that are starting at the homogeneous state. And you can explain this in much more detail in this talk, since I do want to get to the bifurcation points. I'm not going to have time. Happy to talk about this offline at some point. But there's a way to describe really why these curves, why these location curves of pitchfork bifurcations are responsible for this long-term dynamics change. But important is that one of the things that comes out of this whole discussion is that in most cases, these solutions really are not able to make it to the global minimizer. They're really trapped earlier and really converge to limits that don't have the periodicity that you actually would expect from the global minimizer. All right, so much for motivation. That's basically the motivation for trying to do computer-assisted proofs. Unfortunately, for this bifurcation diagram, there's really nothing you can do rigorously by hand, or not a whole lot. You can discuss what's happening close to the trivial solution, but once you're on those secondary branches, trying to establish any of these secondary bifurcation points rigorously is really not that trivial. And so for that, we're turning to computer-assisted proofs. And as I mentioned before, we sort of have a very specific point of view on that. That's obviously related to work that others have done. This is in no way new. This is really just a different slant on these computer-assisted proof results. So this is very much in the spirit of Newton, Kantorovich, Nakao, Plume, and others. Of course, coming from bifurcation theory, the implicit function theorem is somehow the big theorem in the background. And but in its original form, the implicit function theorem really is not useful for computer-assisted proofs. You need a precise solution pair, which you usually don't have. So what we've been trying to do is come up with a version of the implicit function theorem that is much more amenable to computer-assisted proofs, where you don't need a precise solution, but you still get the existence of a local solution branch close by, and that can be done. And I'm just going to describe roughly how that theorem is formulated, and then I'll say a little bit about how we're using this, but I'm not going to go into too much detail here. The basic idea is that we can formulate this constructive implicit function theorem in the general setting. We have Banach spaces for the parameters for x and for y. All we're assuming is that we have some approximation of a potential zero of that equation. And then there's 4 different conditions that need to be verified to get the existence of a unique branch close by. First one, we need to have a small residual, so there needs to be a bound row on the y norm of G evaluated at this approximate solution. We need a bound on the inverse. So if I take the Fréchet derivative at this numerical approximation in the operator norm, I have to be able to bound the inverse. And that gives me a constant k that I somehow have to compute. And then we need Lipschitz conditions. I mean, this is sort of what you would expect. We need Lipschitz conditions both with respect to Fréchet derivative with respect to x, also with respect of the Fréchet derivative with respect to the parameter. And basically, these are encoded in 4 different constants now. So we have a total of 6 constants. Once we can find those constants, basically we can formulate a constructive version of the implicit function theorem. And here it is. If the certain inequality is satisfied, so this, at least in principle, we should be able to do whenever we can make the residual small enough, then I can explicitly compute sizes in the parameter and also sizes in the x variable, so that when I look at the corresponding balls, the product of the balls in parameter space around my point alpha star and in the actual phase space around my point x star with these radii delta alpha and delta x, within that rectangular window, if you want to call it that way, there is a unique smooth graph of a smooth function that contains all the zeros. So it's exactly the formulation of the implicit function theorem. What is different is that we can really explicitly say how large these sizes now are, the delta alpha and the parameter regime and the delta x. And by doing that, you can now basically establish purely through local estimates at one specific point, combined with these Lipschitz constants, a little branch of a solution. And then you can iterate that and basically get computer-assisted proofs for whole branches. Now, important for us was that this constructive implicit function theorem is really a tool more than anything else in some sense. In classical bifurcation theory, you apply the implicit function theorem in lots of different situations. Even if you have a pitchfork bifurcation, the way the proof actually works is that you reduce it to an application of the implicit function theorem. And basically, we're using this constructive version in the same way. So for example, in its original form, it is enough to establish and validate whole branches of solutions, but obviously these branches are not necessarily going to be aligned in the right way. So if we would like to optimize this, maybe we can apply the implicit function theorem in a slightly different coordinate setting, and I'll show this in the next slide roughly, to basically get more efficient branch tracing. You can apply it in different coordinate systems to resolve what happens around saddle node bifurcations. That can be done, and we've talked about this in our 2016 paper. And what we've done recently is that you can also do pseudo-arc length quotation. You just construct a suitable boarded system and then apply this constructive version to this boarded system, and that again allows you to follow branches in the same way. And let me just give you one quick example. If we're trying, for example, to find branches of a problem f of lambda u equal to 0, but we have a solution branch that is sort of not nicely aligned with the parameter direction, if we do have some estimate for the tangent direction, some estimate v star, then I can basically set up a new system where instead of trying to find the parameter by itself, lambda star plus alpha, we're also going to be modifying the x direction sort of through a slanted box that goes around that. By doing that, you can basically, in this new coordinate system, apply the original constructive implicit function theorem, and you therefore get validations of much, much longer branch segments in one go than you would get if you would just apply it in the usual setting. So it's a very easily applicable and very malleable tool that we can use to create these branches. Of course, how do you verify these conditions to actually apply the results? Also there, we're coming from PDEs, and Evelyn and I, and so we sort of like our Sobolev estimates and try to use Sobolev estimates to verify the conditions for this constructive implicit function theorem. And that can easily be done. So earlier this year, a paper came out where we described in detail how we can use a setting where our domain is going to be a subset of H2 of the Sobolev space H2 that incorporates the zero mass constraint and the Neumann boundary conditions. Image space is H-2. And then basically you can easily work out these estimates that you need. The Lipschitz constants are very easy to find using Sobolev embeddings. You can also fairly easily construct a bound on the norm of the inverse. So this basically uses the same kind of techniques that Jan Bowie, Jean-Philippe, Jay are using in their approaches as well. So it's basically a Neumann series argument by looking at a finite dimensional approximation. But by doing that, now you can easily construct these constants, all these estimates. We basically can do them in one go in 1, 2, and 3 space dimensions. So at least in principle, this works in arbitrary dimensions up to 3. Obviously, computationally, 3 dimensions are much more difficult, but at least in terms of the estimates, this is not going to be an issue. And then you can verify bifurcation diagrams, at least away from the bifurcation points. And here are just 2 examples. For most of the talk, I'm going to be sticking to the mass 0 case. So this diagram on the left here, that is something that can be validated very easily away from the bifurcation points. But you can also obviously change to mass different from 0 and get validations of those bifurcation diagrams. Still, with the exception of the bifurcation points. And that's really now what I'm going to be focusing on for the last 22 minutes of my talk. And I want to start with results that are now 4 years old that we did together with Jean-Philippe. How can we validate the bifurcation points directly? Obviously, for saddle node bifurcation points, indirectly you can get the existence of a saddle node bifurcation point by doing the path following around the curve, and just by looking at how the parameter values change, you can infer that there has to be a saddle node bifurcation. But what if we want to pin down the saddle node bifurcation directly? In particular, if we would like to follow that saddle node or pitchfork bifurcations in a two-parameter continuation regime. And so that's really what we're after. So for that, I'm going to be formulating this all at a fairly high level. So let's just assume we have some nonlinear problem, f of lambda u equal to 0. F is just a smooth nonlinear function between Banach spaces. We assume for now, since I'm going to be talking about conditions for these bifurcation points, that we have a precise solution of this zero equation. And let's also call L the Fréchet derivative of the nonlinear operator with respect to U at that particular solution. There's a few assumptions in order to do that bifurcation analysis. I'll definitely assume that we have a Fredholm operator. Fredholm operator just means that the null space has to have finite dimension, and the codimension of the range has to be finite. And in fact, what we'd like to have and what we have in our situation is that we would like a Fredholm operator of index 0. That means that the dimension of the null space is equal to the codimension of the range. And in fact, for the bifurcation results, we're always going to be assuming sort of the generic situation that you would expect, and that is that we assume a one-dimensional kernel, one-dimensional eigenspace. If that's the case, of course, from now on, phi 0 is always going to be the function that will span that eigenspace. And then the range has codimension 1, so I can write it as a null space of an element in the dual space. So let's just pick that element in the dual space. I'll call it psi 0 star, but it's just the element that pins down the range of my function. And of course, the implicit function theorem just tells you if my linearization is not invertible, there could be a bifurcation. You want sufficient conditions for bifurcations, and those have been known for many, many years now. Let me just review what you need for a saddle node bifurcation. Generically, if you look at the derivative of f with respect to the parameter, you would expect that that derivative is not contained in the range, and you can certainly test that with this element in the dual space, psi 0 star. So under this condition, you would expect that you do have saddle node bifurcation. Not quite true. You need another non-degeneracy condition that involves the second derivative. But under those two conditions, and these are really generically satisfied, what you can prove is that lambda 0 u 0 is a saddle node bifurcation point, and that's classical result. Now for us, since we're trying to track saddle node or other bifurcation points in a two-parameter continuation setting, these kinds of conditions are not that easy to work with. I mean, I don't want to have to validate these bifurcations as I'm tracking the whole branch. So we'd like to have a different way of actually characterizing a bifurcation point. And the idea is something, and actually let me skip over that slide. The idea is something that goes back to work in the 80s by Werner, Spence. I'll give more details on the next slide here. And that would be, let's try to reformulate the existence of a bifurcation point as a zero finding problem in itself. And at least intuitively, it's kind of clear what we should have to do. If we have a bifurcation point and an associated eigenfunction, clearly the bifurcation point has to satisfy this first equation, f of lambda u equal to 0. Since phi 0 has to be a kernel function, if I look at the Fréchet derivative and plug in phi 0, I should get 0. That's another equation that should be satisfied. And of course, just looking at these two equations alone is not going to be something that's easily amenable to a computational study, because, of course, once I have one eigenfunction, every scalar multiple is an eigenfunction too, so I need to pin down a unique one to get a unique 0. So let's add a third constraint, and that constraint, let's just pick any element of the dual space of U that just singles out a specific eigenfunction. So it's clear that if I do have a bifurcation point, the bifurcation point together with the eigenfunction has to satisfy this extended system. It's a necessary condition. The question is, can we go back? Is it enough to just look for a solution of this extended system and then infer that we actually have a bifurcation point of the original system? And that turns out to be the case. So this is something where Moore, Spence, and Werner started developing numerical methods for finding and tracking bifurcation points in the 80s. They didn't really prove the converse result that we had down here, but I'm sure it was known to them. They really were more interested in a numerical paper there. But what we did in the paper with Jean-Philippe, Evelyn, and I, was to basically show that if you have an isolated non-degenerate zero of this extended system, that automatically implies these two conditions that give you the existence of a saddle node bifurcation point. So you don't have to worry about these conditions in the slightest. They follow from the fact that you have an isolated non-degenerate zero. And the nice thing is, now we've basically just reformulated finding the bifurcation point as another zero finding problem. And now if I throw in that extra parameter sigma, I can use, for example, the constructive implicit function theorem to easily find branches of these equilibrium solutions, of these saddle node bifurcations. And that can be done. So this is just one example. These are two types of saddle node bifurcations that we had in that equation. In both of those images, U is the solution that's shown in blue. The eigenfunction is shown in red. And at the time, obviously, since Jean-Philippe was involved in the paper, we used radii polynomials to actually establish the branches. But as I said, you can use lots of other ways to do this. You could certainly use the framework of this constructive implicit function theorem as well. All right, now saddle node bifurcations are easy. And the interesting thing is that these extended systems automatically lead to saddle node bifurcations. Now, of course, in view of Sart's theorem, you would expect that those are really the only bifurcations that are of interest. If you have a generic function and you perturb it arbitrarily small, you will basically break up all other bifurcations. That's what Sart's theorem basically tells you. Of course, in PDEs, the situation is not quite as easy. You have inherent symmetries that are coming from your domain. And so that means that in the PDE setting, at least, and also in other settings, if you have some sort of symmetry involved, pitchfork bifurcations can really persist. And in fact, as we've seen, there's lots of pitchfork bifurcations in these bifurcation diagrams that we have in the Diblock copolymer model. So the question now is, can we use the same idea using these extended systems to also validate directly and path follow directly pitchfork bifurcations? And so what we need for that is of course, a framework that guarantees us the pitchfork bifurcations. And this is again, something that has been known for many, many years. If you have some sort of symmetry involved in the equation, then that usually can force somehow these pitchfork bifurcations. And the symmetry that's generally studied in this context is just simple Z2 equivariance. What do I mean by that? Let's assume we have two symmetry operators, one on the domain, one on the range, and usually they're actually the same operators, they're just acting on different function spaces. We'll see that in a few minutes. I want that they're involutions. That's exactly why we talk about Z2 equivariance. And Z2 equivariance just means that the nonlinear equation has the property that if I apply F at lambda and SU, I get S times F of lambda U. I can basically pull out that symmetry operator from the U part of my equation. And in this case, we call this operator Z2 equivariant. And important for us is that once we have these symmetry operators, we can actually decompose our phase space in a canonical way into symmetric elements and anti-symmetric elements. Symmetric elements are all the elements where S of U is equal to U. Anti-symmetric elements are all the elements where S of U is minus U. And you can easily show that this is a direct sum decomposition of your space, and you can do the same thing in the image space. Now, what does that have to do with bifurcations and forcing bifurcations? If we do have a problem of the form F of lambda U equal to 0, and we do have that kind of Z2 equivariance, what we do get is the following. First of all, if we're looking at a bifurcation point where U0 is a symmetric function, then also its image is going to be in that symmetric subspace. But more important for us, if we look at the Fréchet derivative at that particular point, it sends symmetric functions to symmetric functions and anti-symmetric functions to anti-symmetric functions. And in particular, another thing that we're getting out of this equivariance, if we have a one-dimensional null space for our Fréchet derivative, then any kernel function has to be either symmetric or anti-symmetric. It can't be a non-trivial superposition of both. And that's important. If we're in a situation where our solution, the potential bifurcation point is symmetric, but the eigenfunction happens to be anti-symmetric, then in fact I could completely restrict my nonlinear operator to just the symmetric subspaces, and then use classical implicit function theorem to get a branch of symmetric solutions, because I've sort of blocked out the kernel function, since that is part of the anti-symmetric decomposition of the space. And basically, the fact that my eigenfunction lies in these anti-symmetric functions then generically leads to a Z2 symmetry breaking pitchfork bifurcation that will persist even if we have perturbations. And the result that you can prove, there's again a non-degeneracy condition that that has to be satisfied. And under that non-degeneracy condition, you basically get a situation either like the one shown on the left or on the right, and you get this pitchfork bifurcation induced by this Z2 equivariance in the equation. Of course, for us, again, the question is, how can we turn this into something where I can easily apply, for example, this constructive implicit function theorem to follow branches of pitchfork bifurcations? So we'd like to use, again, an extended system. Now, obviously, we can't take the extended system that I just talked about in the context of saddle node bifurcations, because the theorem that we proved in the paper with Jean-Philippe was a one-to-one correspondence. If you have a non-degenerate zero of the extended system, it will give you a saddle node bifurcation, not a pitchfork bifurcation. And it turns out that the way out of this, to find still an extended system formulation that gives you the pitchfork bifurcation, is we actually make the system simpler. All you have to do is in the second component, where we have the function that actually corresponds to our zero along the bifurcation branch, we just have to take those second components and basically restrict them to the symmetric space. But only the second one. Remember, of course, for the result, we need to assume that our eigenfunction is anti-symmetric, but we do need to study this system really on this space R cross U, S cross U. And if we do that, then basically we can prove the following result. Lambda 0, U0 is a symmetry breaking pitchfork bifurcation point if and only if lambda U0, phi 0 is an isolated non-degenerate zero of that system. And in addition, and that's a separate constraint that you have to verify, phi 0 has to be in UA. Okay, but we do need the one-dimensionality of this null space on the whole space. That is important. There's actually examples in our paper that show that if you would also restrict this to the anti-symmetric space, there are situations where you do not get a pitchfork bifurcation. All right, now how do we verify that phi 0 is in the anti-symmetric space? That's trivial, because again, we have a general result that says that every eigenfunction in this setting has to be symmetric or anti-symmetric. So I just have to use a simple computation by, for example, looking at the function values at the endpoints to make sure that it's not symmetric, and then it has to be anti-symmetric. So it's very simple to verify that. And in that way, now we can study these pitchfork bifurcations, and that's what we did in our paper in 2017. Sort of the obvious symmetry that you could use, the obvious Z2 symmetry, is basically a reflection around the midpoint, x equals 1/2. So the symmetry sends a function u of x to u of 1 minus x. So clearly this blue function here is a symmetric function. The corresponding eigenfunction is anti-symmetric. It's odd with respect to x equals 1/2. Here's another example. And in both of these cases, you can validate these bifurcation points, and you can path follow them using this result, using the extended system. And if we're looking at the case mass equal to 0, which I've been doing for most of the time anyway, we can also multiply by -1 because we have an odd nonlinearity. That's a different kind of symmetry now. Now the symmetric function is the one that is odd with respect to this point x equals 1/2. The anti-symmetric eigenfunction is even, and also this one we can follow, and we can get branches. And here are some branches that we could that are all validated through computer-assisted proofs that we did in the paper with Jean-Philippe. All right. Well, that was what we did in 2017. And in that paper, there was one case that we needed to leave open. And at the time, we really had no idea how to do this. We were looking only, for no particular reason, but we're only looking at the parameter range up to 300. And in that whole parameter range, we could validate every single saddle node and pitchfork bifurcation that showed up with one exception. And that one exception is shown here. This is a solution that is odd with respect to the line x equals 1/2, but the corresponding eigenfunction is also odd. So you can't apply this Z2 symmetry breaking result there at all. At the time, it wasn't clear how we could get around this. What's interesting about this function is, even though when you look at that eigenfunction, there's no sort of other symmetry that you can somehow recognize, some other inherent symmetry other than the oddness with respect to x equals 1/2. So that, of course, means that if I take the product of those two functions to compute their inner product, the integral from 0 to 1/2 is going to be the same as the integral from 1/2 to 1, but it turns out, at least numerically, that that integral from 0 to 1/2 is 0, even though it's not automatically clear why should that be forced to be 0. So there clearly is some orthogonality still there, even though we don't quite see what the symmetry is. Unfortunately, at the time, we thought this was one strange exotic case that we couldn't deal with, but in fact, there's lots of those. So when you actually do the path following further out, these are just partial bifurcation diagrams. Now, if you go up to 1600, what's shown here in colored dots and crosses are all the bifurcation points that we have, or the pitchfork bifurcation points, and only the cyan and magenta dots are the ones that we could actually cover with the theory that we did with Jean-Philippe with C2 symmetry. There's lots of bifurcation points, these red and green crosses, where we either have even eigenfunctions with even solutions or odd eigenfunctions with odd solutions. And I'm just going to show a few here. I'm going to go through this fairly quickly. Here's an odd eigenfunction in red to an odd solution, and there's lots of these things. And also what you notice is that there's this very strange structure. The solutions, they're all going to be periodic, but the eigenfunctions, sort of as your periodicity goes up, they basically seem to be approximating a straight line. There's some wiggles in there, but other than that, there's no other apparent symmetry that you can easily see. The question is, how can you address this? So I'm just going to flip through a few more pictures here. Those are the ones where we have even eigenfunctions with even solutions. There's a few more. So we need something new. The question is, how do we study these kinds of bifurcation points? And again, we have two different things to address. One is, how do I actually prove a result that gives me the bifurcation, or the pitchfork bifurcation? And then, of course, I'd like to, again, set up an extended system so that I can use these extended systems to follow the branches. Now, from a purely symmetric point of view, or symmetry point of view, it's not that hard to see which symmetry is broken between the solution and the eigenfunction. Again, let's look at this example here on the lower right. The solution, this is for n equals 11. We have 11 different transition layers for my equilibrium solution. I can easily come up with a symmetry that preserves exactly that function, but not the eigenfunction. And the symmetry, and from now on, I'm going to be only looking at the case mass equal to 0, is the following. We take our function u. Since we have Neumann boundary conditions, I can extend that function u to all of r by even reflections. So now I think of this as a function defined on the reals. And then I can define the following operator Tn. I'm shifting the function to the left by 1 over n, and then negate it. And if I do that, that actually turns that blue function into itself. That's very easy to see. I just shift to the left by one layer. Likewise here for n equals 6. This is clearly the symmetry that is respected by my solutions. Unfortunately, and this is the big problem with this operator, and this caused us some headaches for a while, this operator doesn't act on our function space that we're interested in. Because you can easily look at the eigenfunction here. If I apply that operator Tn to the eigenfunction, I'm getting a shifted function, but it no longer satisfies the boundary conditions. I've left my space that I'm considering with the Neumann boundary conditions. So in some sense, we suspect that this is the symmetry that's responsible for the symmetry breaking, but we can't really use it on the space that we're interested in imposed from our boundary conditions. So how can we get around this? The idea is actually pretty simple. Let's first enlarge the space and look at something larger. Let's look at the space of two periodic functions. If I take a function that has Neumann boundary conditions and extend it to the real number line by even reflections, I get something that's two periodic. Let's still consider the mass constraint, and let's take functions that are locally in H2. And on that space, of course, that operator Tn works perfectly. I don't care about boundary conditions at this point. I just have periodic boundary conditions, and they are certainly satisfied also for the shifted function. This operator acts on the space, and in fact, what we immediately see is that if I shift 2n times, I'm going to get back to the identity. So this is an operator that has a minimal polynomial of t to the 2n minus 1. And now basically we see what's going on. If I have my minimal polynomial, I can factor that minimal polynomial. I mean, this is obvious. I can also pull off this factor t minus 1. And of course, polynomial algebra and linear algebra tells you that once you have this factorization of the minimal polynomial of an operator, it gives you a space decomposition. So I can take my space of periodic functions in H2 and decompose them into the null space of Tn minus I, the null space of this sum of the powers of Tn from 0 to n minus 1, and the null space of Tn plus I. And I call these spaces with subscripts A, B, and C. Important for us is that these spaces, even though the functions necessarily don't work well with Tn, but these spaces are invariant under the operation that sets a function u to u minus a function u of x to u minus x. And that means each of those spaces I can easily decompose into a direct sum of even and odd functions, and that means I can get the boundary conditions back. Basically, all I have to do, and you can prove this very easily, that even functions with respect to x equals 0 in this space H2 periodic on R automatically satisfy homogeneous Neumann boundary conditions, and the odd ones give you the homogeneous Dirichlet boundary conditions. So my original function space, I can decompose also using these polynomial representations of my operator Tn by just taking the restriction with the even functions. And this space decomposition now allows me to really get the result. And I'm going to go through those next 3 slides fairly quickly. These are sort of the 3 main observations that allow us to validate these bifurcations. The first one is by looking at symmetry of functions in these 3 spaces and looking at their symmetry with respect to the midpoint, x equals 1/2, depending on whether n is even or odd, you can actually say in which of those spaces the functions are. There's a distinction between UC and the direct sum of UA and UB. So you can easily figure out, based on the symmetry, in which of those spaces they are. The second important part is that all 3 of those spaces are pairwise orthogonal. Now, of course, for the UA plus UB and UC, you get orthogonality because of the symmetry. One function is even, the other one is odd. If you take the product, you get integral equal to 0. But this is sort of the crucial identity that we needed to understand. If I take a function u that is in UA, and remember that's exactly the symmetry that is respected by my original function, and I take a function v that is in u sub b, which is this null space of these powers of t sub n, their inner product turns out to be 0. And the proof is very simple, and it's really nice. You basically just take your domain, you split it up into pieces of length 1/n, you do a variable transformation. So that pops up, gives you u of x plus kn and v of x plus kn. Well, that is related, of course, to the kth power of the shift operator. Well, u is in UA, so Tn of u is equal to u. So I can pull that out. I can pull the sum back in here. And the v was in the space UB, where exactly the sum is equal to 0. And therefore, I have orthogonality. That's the reason why these eigenfunctions are orthogonal. And this works. I've only shown it here for the L2 inner product, but that also works with the H2 inner product. So we get the orthogonality that we need. And the third sort of observation that's necessary for the result is that if we have an equilibrium solution in the space UA, this null space of Tn minus I, and we have a one-dimensional kernel for the Frechet derivative, then the eigenfunction has to be in one of these 3 spaces, UA, UB, or UC. It's the same result that we had before. And in fact, again, we can easily characterize when is the eigenfunction in which of those spaces. If it's even with respect to x equals 1/2, either it's in the direct sum of A and B or in the space UC, depending on whether n is even or odd. The same thing switches if the function is odd. And if we're in that direct sum, you just need one additional constraint. You need to prove that the eigenfunction is non-zero at 1/2n, and then you're guaranteed that you're in the space UB. And basically, with these 3 observations, you still have to work, and this is what Evelyn and I have been doing over the last few weeks. You can basically now prove a sufficient condition for bifurcation that is exactly in the same spirit as the Z2 symmetry breaking, but now it's created by this Z2n group that we have, this cyclic group. And the surprising thing, and that was really the surprising thing for us, is that in terms of the extended system, nothing changes whatsoever. All you need to do is restrict your second component to this new space of symmetric functions. The proof obviously is going to be slightly different from what we had in the paper with Jean-Philippe, but in terms of actually applying the result, it is exactly the same result. You just need to verify after the fact that the eigenfunction is either in UB or UC, and once you have that, you get the branches. And so what that means is we can really take the code that Jean-Philippe wrote at the time for the paper, just plug in the other solution. You just have to make sure that you stay in this UA space, but basically you get the same branches like we had before. And so in some sense, it really seems that this restricting these equations to a symmetric subspace, as long as you have these sort of other ingredients, and you can sort of really formulate a nice meta theorem here. If you have a certain space decomposition that has certain properties, then you automatically are guaranteed to get a pitchfork bifurcation out of an isolated solution of this extended system. And I'm running out of time, so I just here on this slide just gave the conditions that you need to verify to make sure that your eigenfunction is in one of these two spaces. As I said, it's very simple conditions that you can easily verify you're doing computer-assisted computation. And with that now, we basically can at least treat all of the bifurcation points that we've seen in that equation. Maybe there's other ones that we can't do yet, but we haven't path followed far enough out to see those. But that was it. So thanks for your attention. Here are just a few references. And so the results that I talked about today, they should be done in a couple of weeks or so. You should find this on the archive. All right, thank you.
Thank you very much, Tom. There are plenty of questions or excuse me, there's plenty of time if people have questions.
Yeah, I have one.
Sure.
So it's, well, yeah, wonderful. I really like this meta theorem. It's great. So the identification to find this T sub n equals minus u of x plus 1 over n. Say in general, I mean, I guess you found this map by looking at the patterns, right? I guess.
Yeah, exactly.
And
by looking at the solution, exactly.
Yeah. So if somehow you didn't know which, I mean, you had a pattern and you suspected that there is this kind of map there. I mean, would there be a way to somehow systematically kind of try to find it, this T, or this is really like some sort of?
No, I'm not
you have
sure.
to look at.
I'm not sure. I mean, in this case, that was sort of the thing that we looked at. The problem that really threw us for a loop for a long time was exactly the fact that you leave the space. You can't, you're no longer in the space with the right boundary conditions. And so that took a while to figure out. Once we make that detour, we can sort of come back. But I think this idea in general that if you see a certain pattern and you can somehow see what is the invariant operator that gives you that pattern, looking at these polynomial algebras and looking at the minimal polynomial, I think can give you the way to get that space decomposition.
Right.
And once you have that space decomposition, things are nice. But for the original paper, I don't know. I mean, the way I formulated it here, I always assumed mu equals 0, and in my operator I had that negative sign in there. So I really do need the odd nonlinearity for these results. But in fact, that was really just for the presentation for here and also for the paper. But if you want to go to a case mass different from 0, you can still do the same thing. You can't do the multiplication by -1. You just shift by 1 over 2 by 2 times by 2 over n over. You shift the whole period over, and then you can basically do the same thing again. And then depending on whether n is even or odd, you have different kinds of minimal polynomials. You'll have to treat those separately. But the same result, the same meta result, also works in that setting, even for mass non-zero. And it's the same idea, but once you sort of recognize what is the minimal action that you have on your solution, by working through the minimal polynomial and the space decomposition, you basically can get that result. And as I said, I mean, for the paper, we'll definitely try to have sort of a meta theorem formulation in there that says if you have this kind of space decomposition with these kinds of properties, then you automatically will get both the pitchfork bifurcation and that extended system characterization.
Yeah, that's great. No, because I was wondering, I have a student who has a project, and then we suspect that we have these symmetries, and then we have these kind of operators, but we cannot find them, and it's particle simulation, so it's finite dimensional. But I was wondering if we could somehow solve for the T, your T, and or numerically, or look in a class of problems where you have, I don't know, some linear combinations of translations and. No,
I mean, you see, the problem for us was actually the opposite one. Of course, our first attempt was to figure out what is the symmetry of the eigenfunction. that was the one that we really were after. And to see that this is exactly in the null space of the sum of the powers of the operator, how are you going to find this? I mean, we did find that first, and only afterwards realized that this came out of that whole polynomial algebra thing. But
okay,
yeah.
All right, thank you.
So yeah.
May I ask a question, Thomas? Which is sorry? Yeah. Okay. So it may be maybe a bit naive, but concerning this leaving the space of which in which the Neumann boundary conditions are satisfied. So if you formulate the whole problem weakly, then you don't see the Neumann boundary conditions anymore, right? So you
do still see them. I mean, you still have the first Neumann boundary condition, so you still have evenness with respect to x equals 0.
Okay, so you lose the third order.
You lose the third order, but you still have the first order.
But the first order one remains. Yeah. Yes.
So you do still have the evenness in there.
Yes, that's right. And concerning maybe in the same context, when you just take something like periodicity as symmetry, is that the same? Would that lead to the same idea which you proposed here? This was not so clear to me.
So yes. So in fact, actually, I mean, I had it on the slide. I just went too quickly and sort of went over it. But if you look in the space of periodic functions, two periodic functions, really the group that's acting is actually a dihedral group. So you have the shift, that's the z to n, but that u of x mapping to u of minus x, that gives you the additional generator for the dihedral group. And so you basically have a dihedral group symmetry. And you can definitely use results from equivariant branching and who knows what to study bifurcations on the space of periodic boundary conditions. It was really for us, since we started out and we wanted to study the equation with respect to the Neumann boundary conditions, we had to basically factor it down and go down to this sort of invariant subspace with the even boundary conditions to get that decomposition. But yeah, you could definitely do this on the space of two periodic functions too.
But of course, then you nevertheless you have the trouble with the Neumann conditions again.
That's right. That's right. Exactly.
Okay. Thank you.
Other questions?
I have actually one more, if I may. So there is concerning just existence of bifurcation points, there is the classical Krendel-Rabinowitz result, right? Which also assumes that there is just a one-dimensional kernel, and then there are some transversality conditions and smoothness conditions and so on.
Exactly.
So how do these classical conditions compare with the conditions you have in the computer-assisted approach? So of course, the result of the computer-assisted approach certainly has the advantage that you quantify everything, right? And
well, the classical
says there is a small neighborhood, and you don't know how small it is. But concerning the conditions, that one can compare.
No, the conditions are basically the same, with one caveat. I mean, I think in the classical Krendel-Rabinowitz, if you would apply it to this setting here, where the eigenfunction has the odd symmetry, you're actually in the degenerate case. You don't have the non-degeneracy condition is not satisfied. So in the symmetry breaking case, you really have to treat it slightly differently. So in fact, the Krendel-Rabinowitz result is sort of inherently there, but it would correspond to the case where the eigenfunction is also in the symmetric space, in the same space as the original solution.
Well, of course, you could, of course, try to apply the classical result, Krendel-Rabinowitz result, in these symmetric spaces.
Right, exactly. But the problem is when you, in our setting, the eigenfunction is in the antisymmetric space. The non-degeneracy condition in Krendel-Rabinowitz does not hold.
That's clear. That's
the issue. But no, I mean, and the proofs, of course, are all, it's exactly the same proof as in Krendel-Rabinowitz. I mean, it's really just that we use the symmetry to get the trivial solution in the Lyapunov-Schmidt normal form.
Okay. So if I may continue, you did that in the one-dimensional example because you have this very rich structure of the bifurcation diagram. But I think that you could, so the basic ideas are generalizable easily to the higher dimensional case if you have symmetries at hand.
That's right.
For example, if you are on the unit or on a rectangle, for example, you could just so to say tensorize these symmetries which you have in 1D, and then you could get the same.
Yes.
Because it's not so clear if the problem really shows all these rich.
No, but in principle, yes. The really important part here is the one-dimensional kernel. So you really have to stay away from squares or something. So you would have to break the domain symmetry if you're in 2 dimensions to make sure that you would expect, you know, simple one-dimensional kernels. 2-dimensional kernel is very, very different. And so that definitely wouldn't work here. But yeah, as long as it's one-dimensional, yeah. So for example, if you work on a rectangle and make sure that your bifurcation points have one-dimensional kernel, if the symmetry is the right one, yeah, that should definitely work.
Okay, any further discussion? Well, if not, then let's thank Tom again for a wonderful talk. Tom, thank you.
Thanks for having me. Thanks for listening.